The direct comparison test. Objectives. By the end of this lesson, you should be able to use the direct comparison test to determine if a series converges or diverges. The direct comparison test. So suppose a sub n is greater than 0 and b sub n is greater than 0 for all n, or at least for all n past some threshold, capital N. So let's stop right there and let's think about what that means. So we're going to have two infinite series here. So we have two general terms, a sub n and b sub n. And what this first part is saying is that we need those terms to always be positive for all n. But this portion right here, and it's going to be included pretty much for every test from here on out, we only really care about, again, what happens toward the end of the series. So if the first couple of terms happen to be negative, but then for the rest of the time, right, as we care about what happens towards the end, for all n past some threshold n, big N. So if the first 10 terms are negative, that would be that threshold value, big N. So the threshold value would be 10, but the 11th term on, well, then they're all positive from then on out. So that's just a formal way of saying we don't really care what happens at the beginning of an infinite series. We can add negative a billion, we can add 100 million. It doesn't really matter what happens at the beginning. Positive, negative, that's not going to affect whether or not the end of the infinite series converges or diverges. And then after that, we're further going to suppose that a sub n is less than or equal to b sub n for all n. So if we're comparing term by term, a sub n is always going to be the smaller term, or at least equal to the term from the infinite series involving b sub n. Or again, for all little n past that threshold number, big N. So the direct comparison test has two parts. It says that if the sum from n equals capital N to infinity of b sub n converges. So remember, we were assuming that b sub n is the bigger one. So if this infinite series converges, then the sum of the infinite series with a sub n as the general term also has to converge. So if the bigger series converges, then it must be true that the smaller series converges. If term by term, a sub n was a smaller number than b sub n. Again, past that threshold value n. And then if the sum of a sub n diverges, then the sum of b sub n must diverge. So if we're adding all these infinitely many terms of a sub n, which was the smaller one, and all of those infinitely many numbers diverge, so the sum of that's going to go to infinity, then there's no way that if I add up numbers definitely bigger than that, that's going to converge. So that has to diverge as well. So here's the informal version. So given an infinite series, if we can term by term find a bigger series that converges, anything smaller than that will also converge. And if term by term we can find a smaller series that diverges, then anything bigger than that must also diverge. So the warning here is that we want to make sure that inequalities are facing the right way. When thinking about whether or not you want to use a direct comparison test, I want you to think about this door analogy. So suppose Brian is 6 feet tall and Anna is 4 feet tall, and they are about to walk through a door, and we don't know how tall the door is. We do know that if Brian can fit through the door at 6 feet tall, then Anna can fit through the door as well. We also know for sure that if Anna cannot fit through the door at 4 feet tall, then Brian cannot fit through the door at 6 feet tall. But there are some inconclusive cases, some cases where we're not sure what would happen based on who goes through the door first. If Brian cannot fit through the door at 6 feet tall, we don't know whether or not Anna can fit through the door. So there's two possibilities. If Brian can't fit through the door, well, the door might be 5 feet tall and he's 6 feet tall, so he can't fit through it, but Anna can fit through it at 4 feet tall. But if the door is 3 feet tall, Brian definitely cannot fit through it, but Anna at 4 feet tall cannot fit through it either, so that would be considered an inconclusive case. And the other inconclusive case is, well, what if Anna can fit through the door? We don't know whether or not Brian can fit through it. So if Anna can fit through it at 4 feet tall, so let's say the door is 5 feet, then Brian can't fit through it. But if Anna can fit through it because the door is 10 feet tall, well, then Brian can fit through it as well. So we're just not sure about the following two cases. So the point here is that you have to think about the direction of the inequality on the direct comparison test in order to make sure that it really is working for you to determine convergence or divergence. So this is a good example to think about because it's definitely something that we can visualize a little bit more. Alright, so now some examples. We want to apply the direct comparison test to each of the following series. So here I have the sum from n equals 1 to infinity of 1 over n squared plus 5. So without this plus 5 here, 1 over n squared looks like a p-series test. So the hardest part about the direct comparison test is deciding what to compare your infinite series to. So you want to, by rule of thumb, try to see, well, what does this look like? And then whatever it looks like, can you easily determine the convergence or divergence of that series that it looks like? So 1 over n squared, I can definitely determine that it converges by the p-series test. So we're going to go ahead and compare the sum from n equals 1 to infinity of 1 over n squared plus 5 to the sum from n equals 1 to infinity of 1 over n squared. So let's go ahead and state for now that we know that this series on the right is a p-series that converges. So by the p-series test, since 2 is greater than 1, this series on the right side converges. So now that we know that this series on the right converges, let's decide what inequality we want in order for the direct comparison test to actually help us. So if this series on the right-hand side converges, I want to make sure that the series on the left is less than or equal to the series on the right. So in other words, I want the one on the right to be bigger so that because it converges, it will force anything smaller than it to also converge. So here's what I want. So now let's for a second compare just the general terms. So I want to know that 1 over n squared plus 5, I want it to be, but I'm not sure that it is, less than or equal to 1 over n squared for every single n that I plug in. So now let's think about these in terms of fractions. So if I were to compare two fractions, and I'll just write any two fractions with the numerator of 1. So if I have 1 over 3 and 1 over 2, well, 1 over 3 is less than 1 over 2 because 3 is bigger than 2. So in other words, instead of wanting to figure out whether 1 over n squared plus 5 is less than or equal to 1 over n squared, what I really want is I want n squared plus 5, the denominator of this fraction, I need that denominator to be greater than or equal to n squared. So again, we're still questioning this. We want to know whether or not this is true. But in comparing these two now, so if I plug in different values of n, this on the left side, n squared plus 5, is always going to be 5 greater than n squared. So in other words, n squared plus 5 is definitely greater than or equal to n squared. So if the denominator n squared plus 5 is bigger than n squared, then this fraction 1 over n squared plus 5 is definitely less than or equal to 1 over n squared. Now, the other thing you can sort of think about, even though it's a bit more tedious, is just plugging in particular values. So let me erase this portion for a second. And let's say we were, at this point trying to compare these two general terms. So my starting index is 1. Well, let's see what happens at n equals 1. So the left side is 1 over 1 squared plus 5. So 1 plus 5 is 6. And the right side is going to be 1 over 1. So 1 over 6 is definitely less than or equal to 1 over 1. And then we could try it with a couple terms, because really what we're trying to do is convince ourselves that this is the correct direction the inequality goes. So just to do one more, n squared is 4 plus 5 is 9, so this is 1 over 9. Is that less than or equal to 1 over 2 squared, 1 over 4? Yes. So both of these work out, and this is going to hold the correct inequality that we need. So then now what we can say is that this series on the left, so let me go ahead and erase this, what we would say is that by the direct comparison test, this series also converges, since 1 over n squared plus 5 is less than or equal to 1 over n squared. So the direct comparison test is now quite a bit more work than some of the other tests that we've been doing, because we need to find a series to compare the original series to. We need to know whether that series that we chose converges or diverges, so we want to pick one that we know by a different test whether it converges or diverges. And then we need a particular inequality to hold, or else we arrive at one of those inconclusive cases that didn't help us in the first place. And then once the inequality holds, then I need to state that my original series does either converge or diverge based on the inequality. So I would definitely need to show all of this work in order to correctly apply the direct comparison test. Alright, so now I have the sum of n equals 2 to infinity of 1 over natural log of n. So first, the starting index here is 2, not 1, because if I were to substitute in 1, natural log of 1 is 0, and this general term would be undefined. So we have to start our index off at 2. And now we have to find a series to compare this infinite series to. And this one, 1 over natural log of n, doesn't look like any of our other series, but one of the easiest things I can compare a series to is the harmonic series, 1 over n. So let's go ahead and try that. We're going to compare the sum of n equals 2 to infinity of 1 over the natural log of n to the sum of n equals 2 to infinity of 1 over n. So even though my starting index here is 2, it doesn't matter. We still have the harmonic series that is going to diverge. So we want to say that this diverges because it's harmonic. You can also say this diverges because it's a p-series with p equal to 1, either way, but you want to conclude why this series that you chose either converges or diverges. And now we have to decide the relationship between the general terms. So here's what we want. So because the series that we chose to compare it to diverges, what I want is I want the other series that I'm trying to decide to be greater than or equal to the series that I chose that diverges. Because if I have a series that diverges, then anything bigger than it, term by term, must also diverge. So here's what I want. So let's go ahead and pull out the general terms again. We're comparing 1 over the natural log of n to 1 over n. And we're asking ourselves, is 1 over ln greater than or equal to 1 over n? So again, this is the same as comparing whether or not the natural log of n in the denominator, I would want this to be smaller than, less than or equal to, n, in order for this original inequality to hold. So is the natural log of n less than or equal to n for all n values greater than or equal to 2? So to think about this inequality, because we wouldn't be able to use our calculator to plug in these different values, we would use our knowledge of graphs. So I can think about these graphs as natural log of x and x. So x is just the linear function through the origin, and then natural log of x looks something like this. So in other words, is the graph of y equals x always going to be greater than or equal to natural log of x? Yes, this graph is always above natural log of x. So this inequality holds. The natural log is less than or equal to n as I look at values for n greater than or equal to 2. So this is 1 right here, starting at 2. Yes, definitely the natural log graph is going to be below the graph of just the identity function. So since this inequality holds, I know that this inequality will hold. So this is no longer a question mark. 1 over natural log n is greater than or equal to 1 over n. And again, this is a process where you are convincing yourself that this is true. So this knowledge of graphs is what you need to convince yourself this inequality holds. If this inequality did not hold, then this test would be inconclusive. But because it did, because this series diverges, and I just showed that the general term, 1 over natural log n, is greater than or equal to 1 over n, by the direct comparison test, because this inequality holds, we have that this original series diverges. So by direct comparison test, since 1 over natural log n is greater than or equal to 1 over n, the original series diverges. Alright, so now the sum of n equals 1 to infinity of 1 over 3 to the n minus 1. So hopefully you can see here this looks a lot like the sum of 1 over 3 to the n, which is geometric. So let's compare the sum from n equals 1 to infinity of 1 over 3 to the n minus 1 to the sum from n equals 1 to infinity of 1 over 3 to the n. And so remember, this is really like 1 over 3 as a quantity to the n. So let's go ahead and state that by the geometric series test, because 1 over 3 is less than 1, this series on the right converges. So in order for us to use the direct comparison test here, let's write the inequality that we want. So because this series here converges, I want this series on the left to be less than or equal to this convergent series, because if I have a series that is smaller, it's definitely going to have to converge as well. So now we're trying to show that 1 over 3 to the n minus 1 is less than or equal to 1 over 3 to the n. So again, instead of making this comparison, let's go ahead and think about the denominators instead. So I would need the denominator 3 to the n minus 1 to be a bigger denominator than just 3 to the n in order for these fractions to compare in a less than or equal to fashion that we would want. So now, is 3 to the n minus 1 greater than 3 to the n? So hopefully you're thinking no, because here 3 to the n and 3 to the n are the same, but over here if I'm subtracting 1 every time, there's no way that 3 to the n minus 1 is going to be greater than 3 to the n. So this is not true, which means that this is not true. So what we wanted to happen up here to compare these two series is not accurate. So the direct comparison test that we applied is inconclusive. So the direct comparison test here is inconclusive. It doesn't tell us anything. This is one of those cases where I don't have the inequality facing the right direction to tell us anything. So in fact, this series on the left is greater than or equal to this one that we know converges. So if this smaller series converges, if I add up a bunch of numbers that are bigger than that, then how would I know whether or not those numbers are going to add up to a finite number if those numbers are bigger? So the direct comparison test in this example is inconclusive. So it's important to start out by knowing what you want to happen for the direct comparison test to be useful, but don't always force it. It's not always going to work. So you want to know what you want, but you want to know when you fail to achieve what you want, and making the direct comparison test not helpful. Alright, so now I have the sum from n equals 1 to infinity of 5 to the n plus 1 over 2 to the n minus 1. So here it looks like we should compare to the geometric series 5 to the n over 2 to the n. So we're going to set up the sum from n equals 1 to infinity of 5 to the n plus 1 over 2 to the n minus 1. We're going to compare that to the sum from n equals 1 to infinity of 5 over 2 as a quantity to the n. So here, 5 over 2 is greater than 1. So by the geometric series test, I know that this thing diverges. So if this infinite series diverges, then in order for the direct comparison test to be useful, I'm going to want this series on the left to be greater than or equal to the one on the right. So if I have a series that diverges, the only way the direct comparison test is going to be useful is if I can show that the series I'm trying to compare it to is bigger than that, because something bigger than a divergent series must also be divergent. So let's go ahead and now try to compare 5 to the n plus 1 over 2 to the n minus 1. Let's compare that. Is it greater than or equal to, we're questioning it, 5 to the n over 2 to the n. Alright, so here, if it's a little hard to see, let's go ahead and start to plug in values. So let's say n equals 1. So on the left-hand side, I'm going to have 5 to the 1, which is 5, plus 1 is 6. And then if I plug in 1, 2 to the 1 is 2, minus 1 is 1. And then on the right hand side, 5 to the 1 over 2 to the 1 is 5 over 2. So yes, 6 over 1 is greater than 5 over 2. So this is true. And then if I have n equals 2, so 5 squared is 25 plus 1 is 26. And then 2 squared is going to give me 4 minus 1 is 3. And if I plug in 2 here, I'm going to get 25 over 4. So now let's try to think about these as mixed fractions just to compare them. So 3 goes into 26 8 times, and I have 2/3 left over, whereas 4 only goes into 25 6 times with a remainder of 1 over 4. So 6 1/4 is less than 8 2/3, so we have greater than again. And again, as we get better comparing fractions here, we didn't really have to plug in numbers to test this. We can see that the numerators, well, 5 to the n plus 1 is always going to be greater than or equal to 5 to the n, so that would make this fraction on the left bigger. And then similarly, this denominator, 2 to the n minus 1, is always going to be smaller than 2 to the n. And when I have a smaller number on the bottom, that makes for a bigger fraction. So here we just tested the numbers to get some intuition, but ultimately the inequality we wanted was true. So those are no longer questions, and we can say by the direct comparison test that the series also diverges. Alright, so now for this last example, and this is a trickier example, I have the sum from n equals 6 to infinity of n minus 5 over 2 to the n plus 1. So the series that I'm going to compare this infinite series to is going to be the sum from n equals 6 to infinity of n over 2 to the n. So we're going to have the sum from n equals 6 to infinity of n minus 5 over 2 to the n plus 1. And we're going to compare that to the sum from n equals 6 to infinity of n over 2 to the n. So let's talk about that starting index real fast. In the previous couple of examples, we kind of glazed over the fact that we were going to have positive terms in all of these comparisons, because that's the only way we can use the direct comparison test is past a certain point we have all positive numbers. So here, the starting index is going to be 6, because you can see as we plug in 6 into the numerator, 6 minus 5 is going to give us a positive 1. So that's why we're starting off this one at 6. But for the other ones, just to go back and touch on that point, all of those were going to give us infinite series with all positive terms as well. So we can apply the direct comparison test, and that needs to be one of the first things you ask yourself if you are going to use that test. So now in this last example, the reason why this one's harder is because this series that we're going to compare the original series to isn't as obviously convergent or divergent. So this test, we have to do a different test to determine whether this one even converges or diverges. And the test that we're going to use there is the ratio test. So here what we're going to do off to the side is the limit as n approaches infinity of n plus 1 over 2 to the n plus 1. So that's a sub n plus 1 over, it would be n over 2 to the n. But I'm just going to go ahead and write that as 2 to the n over n. So I'm just going to skip that step of multiplying by the reciprocal here. And this would be in absolute value bars. So now here, this 2 to the n plus 1 is 2 to the n times 2. So this 2 to the n and this 2 to the n would cancel. So what I really have here is the limit as n approaches infinity of n plus 1 over n. So I'm going to keep those similar terms next to each other. And then I have a 2 in the denominator, so I'll go ahead and write that as 1 over 2. So since these degrees match, I'm taking a limit at infinity. I drop the absolute values because everything we're talking about here is positive. So this limit is going to converge to 1/2, which by the ratio test, since this value is less than 1, the ratio test tells us that this series converges. Alright, so now that I've decided the series on the right converges, if I want to use the direct comparison test, what I want to happen, the inequality to be between these two, is I want this one on the left to be smaller than or less than or equal to the one on the right that I found definitely converges. So now what we have to do is compare the general term, n minus 5 over 2 to the n plus 1. I want that to be less than or equal to n over 2 to the n. And again, as we get better with fractions, we're going to notice that this inequality holds true. Because if I want this thing on the left side to be smaller than this thing on the right, well, I need the numerator to be smaller. So n minus 5 is going to be smaller than n. So I'm subtracting 5 from that n quantity. The top is smaller. And I want the bottom to be bigger. So 2 to the n plus 1 is bigger than 2 to the n. So this inequality definitely holds. So because this is true, by the direct comparison test, this original series also converges. And again, we had all positive terms, so we do want to make sure and note that in order to use a direct comparison test, I do need positive terms past a certain number. And then we had to show that the series that we were going to compare it to converged using a completely different test. So this would be considered a harder example of using the direct comparison test.